Okay, hello everyone, Clarke Towson here. I'm the CEO of INTJ Billing. In this video today, we're going to observe some real world ponding behaviour, how water behaves in Cullen Court. So remember, here's Cullen Court here. This is the Engeny map, the Engeny model, which is based on Melbourne Water's model, which I've proven is invalid. Yeah, so today we're going to watch some videos, and what I've done, I've captured some security camera footage of the October 26th rainfall event in Cullen Court, and we're going to go through this because what you're about to see is real stormwater behaviour at 7 Cullen Court, not a model, not LiDAR from years ago, but the actual physics of water flow captured live in the real world. Right, and at the moment you understand the governing equation of flood modelling, you'll see instantly why the special building overlay on 7 Cullen Court cannot physically be correct. Right, so if you'll remember, we have our most important Navier-Stokes equation, the depth averaged momentum equation. Remember, I'm not going to go fully into the equation again, but we've got partial u, partial t, plus u dot del u equals minus g del h minus g s sub f. Okay, depth average momentum formula. Right, and of course every hydrologist, as I've said, in Australia uses this formula. Every two-flow model is governed by this. Melbourne Water uses it. Engeny uses it. Right? We use it in CFD work. Okay, my former colleagues at DST Group used it. Still use it today. And of course, that single equation exposes something devastating about the Melbourne Water and the Engeny model. Right? So here's our video, and you'll see. In the video, I've placed this overlay. Okay, so this overlay, this is a polygon, blue polygon that I've created. When I play the video, you'll see how the water ponds up to here, and I've placed these arrows here as well, showing the land here, and you see the crest here for the curb. So remember, this is council land. We've got the driveway here. Remember, with the 30mm lip. And of course, the direction of the flow from the driveway is to the road, okay, to the road. And this direction here, this arrow here, we've got where we flow into this direction, into the council pit. Okay, I'll just go back one just quickly for the Navier-Stokes equations, right? So the key term, of course, is negative g del h. Right? Gravity acting on the gradient of the water surface, which tells the water which way to move. Right? Water flows down the hydraulic gradient, never up. Right? So the sign of del h controls everything. Right? Very important. So if del h is negative, water accelerates downhill. If del h were positive, that would imply water is accelerating uphill, which of course is physically impossible without applied pressure. Okay, and of course this destroys the SBO at 7 Cullen Court. Right. So here's our video. Let's press play on it now, and let's just sit down and watch. So the video I've sped up 9.5 times. Okay. So remember, this is the October 26th storm event, okay, in Spotswood. It was a major storm event for Melbourne, and I captured it on my security cameras, as well as I went out in the rain and captured it on my iPhone. So you can see, right, we're just starting to rain now. It's just starting off, and as the storm starts to make its way over, what you'll see is, so here's our blue polygon. You'll start seeing the blue polygon fill up with water. You see the behaviour of the water in Cullen Court. See, as we're filling up here, we're going to make it, water's going to make its way up to this section of the road and around, right? But of course it doesn't overflow the curb, right? Got a downward slope here. Okay. The driveway, remember, 1 degree gradient. Okay. So you can see major amount of water, big storm, right? Curb, higher elevation here. Okay. So meaning the surface gradient del H for the Navier-Stokes equations here is negative toward the road, not towards the property. Navier-Stokes tells us the water must accelerate downhill along the negative gradient. You see it's going downhill there, right there, see? So it cannot climb over this high verge here onto the council verge and then through onto my mother's property at 7 Cullen Court. But the model, remember the Melbourne water model that makes up the SBO, the Engeny model, requires the surface, water surface to do exactly that when you look at the SBO, right? So the SBO is incorrect, right? So the model violates the Navier-Stokes equations, in particular minus G del H, right? So all right, that's our video 1. Let's move on to our next video. So here's our TRZ2 zone block, right? The front block, which is private property. Here's our council verge here, right? Remember, private property is where the follows the line of the fence line. Okay, so there's a stake in the ground around about, might be a little bit back here. It's back here. So property goes there, and then like that, and the rest of this is council verge, right? So let's press play on this video. You'll see, again, we've got the blue polygons here, which I place as an overlay. Got the direction of the land. You see it slopes down. Okay, so in other words, this is higher ground than the road bowl. Okay. Of course, the curb is the containment well, or sorry, the containment wall is the curb. Roadway is the depression, right? So there's no physical mechanism under Navier-Stokes for flow to reverse uphill over the curb and onto the block. So you can see, pouring with rain now, you see the blue polygons filling up, and yet, look at this, we've got no water flow over the curb. Of course we don't. Okay, there's no physical mechanism under Navier-Stokes for flow to reverse uphill, cover the curb and onto the TRZ2 zone block. Right, but remember the Melbourne water model, the Engeny model, says that it does. How can that be, right? So the model violates the governing equation. You can see here, it's pouring with rain, and yet no overland flow, right? It's very interesting to see this, isn't it? Real world behaviour during a storm, during a major storm event, right? And how water actually behaves, not in a model, but how it actually behaves, right? So this security camera footage, as well as my overlays and everything, I think are very, very important. I'm very glad that I set all this up, right? You can see here, here's our polygon. That's where we get our nuisance ponding after all storms, and then it takes a while for it to dissipate. Where it dissipates, the water flows along the gutter line down this direction. Right. So remember, our council pit is to the right. So we've got the driveway here, and then further right we've got the council pit. So here's our nuisance ponding. Okay. So this is the real world behaviour of water during storms in Cullen Court. Real world, not a model, real world. So of course, for Melbourne Water's SBO to be correct, water at 7 Cullen Court must accelerate uphill against gravity over a raised verge against the hydraulic gradient shown here in real footage, right? It's a big curb, you know, to get those curb ramps, to get my trailers up and over it, okay? So as I said, you know, the model is incorrect. You know, for it to be correct, as I said, water would have to accelerate uphill against gravity over a raised verge, against the hydraulic gradient, okay? And of course that would require negative friction slope, negative gravitational slope, and a positive acceleration uphill. You know, it cannot happen. All of those things contradict the Navier-Stokes equation, okay? Navier-Stokes momentum equation. So the model is predicting behaviour that's physically impossible under classical fluid dynamics. All right. So my two videos, you know, that they end the special building overlay, the SBO over 7 Cullen Court. Flood modelling standards worldwide require that real observed hydraulics override model predictions, right? And here the governing equation and the observed footage, okay, agree that the model, remember the model, the Melbourne water model, the Engeny model, is the outlier. So it's not a discrepancy, this is a falsification. The SBO polygon fails because it requires an inverted gradient, violation of the physics that the model itself is supposed to obey, right? So our real world behaviour, okay, real world behaviour during storms, okay. Water flows downhill, not uphill. So here's our arrow. You can clearly see water flowing down the hill, right? So we're getting full up here. There's heaps of water that's falling from the rain event, right? We've got our ponding, and then as you see, water makes its way downhill, straight down into the drain, right? Remember this section here, council verge. The front section of the driveway is also council. Okay, it's not on tidal, not on tidal. Okay, downward slope from the garage, the driveway, right? 1 degree slope. Water runs off into this drain here, right? So water's flowing downhill, not uphill. The driveway crest, as I said, hydraulic high point. The driveway crest. Remember the 30mm lip. Okay. The roadway is the true flood storage zone. The verge is too high to overtop. Remember, here's our verge here. And remember the verge on the TRZ2 zone block, right? Our two verges, right? The verge goes all the way here, okay? The TRZ2 zone block remains dry, as does the main property, right? The pit receives all the flow, right? So this pit here, okay? So the predicted flood pathway is physically impossible. And the Navier-Stokes equations prove it. Right. Here's our Engeny map. You can see it's incorrect. You can see it with your own eyes, right? You can see it. Here it is. Here's the video. Actual behaviour. It looks nothing like the model, right? It looks nothing like the model. So anyway, I just wanted to create this quick video today. I hope that you enjoyed it. I'm Clarke Towson, CEO of INTJ Billing.